Hey guys, this is essentially a continuation of isotopes and atomic mass. What this video is about is learning how to calculate the mass number that's found on the periodic table. Remember, I told you that isotopes all have different masses, and you have to utilize the mass number that's next to the hyphen and hyphen notation for the isotopes. That's where these masses come into play when we're calculating the mass on the periodic table. Now, the masses on the periodic table are calculated very similar to like grades in a class. Like you have lab, which would be like 10%, um, quizzes, like 25%, plus tests, which are 45%, and then you have participation, which is 5, and then you have homework, which is 15, and the sum of that is 100. Okay, so you take all your grades that you got for that individual lab, homework, test, and you multiply it by the percent. And you guys all know how to do that. This is very similar. Now, the mass number of an element is a weighted average mass of the atoms in a naturally occurring sample of the element. Let's look at oxygen. We're going to do two examples in this lesson. So, oxygen on the periodic table has an average mass of 15.994. This number is calculated from its isotopes weighted average. So let's take a look at the isotopes of oxygen. Okay, so there's three. You have oxygen 16, 17, 18. Now, you have to be very careful with these. Sometimes they come, and most of the time, with the atomic mass unit, the actual mass of the single atom. Okay? Or you can get the kind of rounded number from the mass. What we did with the isotopes, we were using the rounded, but now we're getting more precise with these numbers here. So at the bottom, note, if you are given the mass AMU, use that. That takes priority. If not, use the mass number next to the isotope. So if you have the mass, the actual mass of the atom itself, use it. If you don't have it, use these three numbers. Very simple. You have to remember that. Okay, how do we know how much of each isotope is present? That's a really good question. Well, scientists pondered on that and they figured it out. They did a lot of testing. There's something called percent abundance. And that is the percent that the isotope exists in a sample of a particular element. Okay, they sample an element and they from different parts of the world or different elements, wherever they're shipped in, they check them and out comes some results, and the results tell us these percents for oxygen. So when you have oxygen, you're going to get these three isotopes, and most of the oxygen is going to be oxygen 16, a little bit 17, and a little bit 18. Now these percent abundances will be given to you every time we do an average atomic mass calculation. Otherwise you can't do it. Now, we're going to actually have to change percent abundance into a decimal form, a usable form. Okay, so if your calculator has a percent key, that's cool. If it doesn't, we have to divide by 100, but we'll explain that in the next steps. Okay, so these are very simple steps. You have to follow them step by step in order to get the proper result. Now, how do we calculate the average atomic mass? Well, I created a little table that we can refer to. Okay, there's directions in the book, and we're going to kind of follow them more or less verbatim. Very simple. It's a little strange at first, but when you see what we're doing, it's actually very easy. Okay, whoa, let's look at this here. That average atomic mass can be calculated by multiplying the atomic mass by its relative abundance. Okay, what we just saw was percent abundance. Now we need to do the relative abundance. Relative abundance is where you convert the percent abundance to a decimal form. So you either use the percent key or divide by 100. And then once you do that for each of the isotopes, you will add up the results. Then finally, round your answer to 2 decimal places. So we're going to take a look at the step-by-step results here. Okay, so I created a little table. Now, we have your 3 isotopes, and here's your atomic mass unit, which is the weight of each one of these isotopes. Here's the percent abundance. Now, converting percent abundance, like it says in the above paragraph, convert percent abundance to relative abundance, which is essentially the decimal form. So you can take 99.757, hit the percent key. You'll get this right here, 0.99757. Or you can divide this number by 100 if you do not have the percent key. If you have a graphing calculator, there's a mode you have to go to do that. Okay, so if you're 0.038, you can hit the percent key or divide by 100 and you get this. 0.205, hit the percent key or divide by 100 and you get this. Now, what do we do with these numbers? It's very important. We want to find the mass of each isotope. And it says up here, by multiplying the atomic mass by its relative abundance. So we can multiply by the atomic mass by its relative abundance. So we're going to take this number here and this number here and multiply it for each one of the 3 isotopes. And we will get this right here. Okay? This is a big number. These are small. This is a big number because the relative abundance is higher. Obviously, it's mathematics. Then we add up the results of these 3. Okay, and we get 16. And that is the mass that's associated with oxygen on the periodic table, or very, very close to it. Okay. Now, let's look at another example here. On your own, calculate the average atomic mass of cesium. Okay, you have your percent abundance, and then you have your isotope with the atomic mass units here. So simply you just convert these to a decimal and then multiply it by these numbers here and then add them up. Okay, so checking your work. You have this table here. You have your relative abundance. You multiply the relative abundance by the atomic mass unit for each one of them, and you get these 3 numbers right here. Then you take the sum of these and you get 132.85. And you can check the periodic table to see if you're right. It's like a self-check. Okay, that's how it's done. All right, guys. Thanks for watching.